Let's do a little practice with physical applications of logarithms and exponents. And at this point, it doesn't matter whether we're using log base 10, natural logarithm, any other logarithm, or an exponential function with an integer base or with base e, it's all the same. So problem number 1, the pH scale. One of the reasons logarithms are helpful is that they help us take numbers that are kind of wacky in terms of being way too big or way too small and project them into a range of numbers that makes us more comfortable. So the pH scale goes from usually 0 to 10. In extreme cases, I guess you can have a pH larger than 10. But what it does is it takes actual concentration measurements that are very small numbers and puts them into something more intuitive. And in particular, the formula that we use, which you should have seen already before you came to this video, is like so. So the item in brackets is the concentration of hydronium ions, which is what makes things acidic or non-acidic if there's a lack of them. This is a very, very tiny number. The log base 10 of this number is asking what power of 10 will result in this number. Now, since this number is very tiny, we actually need a negative power of 10, like 10 to the negative third, 10 to the negative fourth. And so the log of this small number is itself a negative number, and so we throw on an extra minus sign so that we're doing the negative of a negative value, which makes the whole thing positive, and ta-da, there you have a pH, usually on a 0 to 10 type of scale. And so here, there's only two options. Either you're given a pH and you're asked to calculate this concentration, or you're given this concentration and you're asked to find the pH. That's the only two ways this is going to work. And right here we have a problem where we're told the pH of baking soda, which is not acidic, it's alkaline, is 8.3. What's the corresponding concentration of hydronium ions? So we're given the pH value of 8.3, and we are asked to find the unknown concentration of hydronium ions. So we need to dig this out. There's two ways to proceed from here. They are both equivalent. One is I can just remember the definition of logarithms. First let's move this minus sign over before I get carried away. Okay, so I can either remember the definition of logarithms, and I would read this out by saying, if the log base 10 of this item is negative 8.3, what I've got here is a base of 10, a result of this, and an exponent on 10 of this. And so I could write that as, just recast it, as 10 to the negative 8.3 is the concentration that we're actually looking for. That's just sort of unraveling logarithmic notation itself. The other way I could do it is by a more procedural algebraic thing. I was going to say procedural algebraic process, but that would be redundant and repetitive. So here what I can do is I can forget the definition of log for a minute. I can just say, look, I've got an equation. I need to dig out this h plus thing. What's in my way? Well, the log is in my way. Well, if a logarithm is in my way, I can get rid of it by applying its inverse function. What is the inverse of log base 10? Well, it's the exponential function with base of 10. And so just algebraically, I can say I need to eliminate this logarithm from the right-hand side, and therefore I'm going to apply the inverse function by raising both sides of my equation to 10. So I'm applying the exponential function, which is the inverse of the logarithmic function. And the whole point of that is for these two inverse functions to eliminate each other. And so when the 10 and the log eliminate each other, we are right back there. And so the concentration of hydronium ions is 10 to the negative 8.3. And if you want to see that out in its decimal form, just go push some buttons on a calculator. It's a very tiny number. All right, now let's check out an example of radiocarbon dating. This is exponential decay. It involves the exponential function with base e. This is the partner function of the natural log. So the natural logarithm and this exponential structure are inverse functions. So perhaps if we're eventually going to solve for something and we need to eliminate this e, perhaps we're going to end up applying a natural log. Let's find out. The items in this equation are an initial amount of radioactive material and a final amount after a certain time gone by. This number here is the decay constant, which is just the tuning dial that tells us how fast or slow the stuff decays. So we are told there's a sample that's lost 77% of its original carbon-14, of the original amount of the radioactive material. How old is this thing? So we know something about the current quantity versus the starting quantity. We need to find out how much time went by. Now, we're not told specifically an initial amount and a final amount, but we are told enough. We're told that we have 77% of the original C14 left. In other words, if we started with 1 unit of this C14, there's now 0.77 units left. Or we could have just written Q naught and 0.77 Q naught, and the Q naughts would cancel. We could have pretended we started with 500 units of carbon-14 and then calculated 77% of that and put it here. And no matter which way we built it, we would still reduce to just a comparison between the scaling of 1 to 0.77, and then the rest of this looks the same. Don't lose any zeros in that exponent. There's a lot of them. Now I can divide both sides by 1. That's not hard. There we go. I'm looking to solve for t. The t is buried up in the exponent. To get to it, I need to eliminate this exponential base, which means I should apply the natural logarithm, the inverse counterpart, to get rid of it. And so I'm going to apply that natural log of both sides. Like so. The whole point of that now is that this natural logarithm and the exponential function are inverses. They wipe each other out, just like the square root and x squared. And so I'm left with the natural log of 0.77 equals negative 0.000121 t, or t equals negative natural log of 0.77 over 0.000121. Scoot it up. And you might say, wait, how can t end up being negative? Well, it's actually not negative, because the natural log of 0.77 is going to be a negative value itself. And so this will be negative. And so it's good that we have this floating minus sign here, because that will take this negative number and turn it into something positive. And I will calculate this number and put it on the screen. Poof! The numbers have been crunched, and it turns out that the value of t is 2160. And so, since there was a nice question, we give a nice answer by reporting that this sample of carbon-14 is 2,160 years old.